Hello everyone, good morning. My name's Peter. I've worked at ARM for about 25 years now. When I first started, we were working in ARM's only compiler team, and that was working on a fully proprietary toolchain. 25 years later, I'm now one of many compiler teams within ARM, many of whom using LLVM, and we're now maintaining a fully open source toolchain, most of which provided by LLVM, hopefully all of which will be provided by LLVM in the future. Now to start with, I'd just like to explain a little bit about ARM's history, so you can, just so you know where our proprietary toolchain came from, what it was aiming at, because the business context at ARM has changed quite a lot in the sort of past 40 years it's been around. So without any further ado, I'll go on to the next slide. So set the Wayback Machine to 1985, and there was a company that you probably only have heard of if you were around about 50 and British, called Acorn. Probably somebody like me, anyway. But there's a computer called the Acorn Archimedes. This was released in 1987. This is sort of, I guess, a contemporary of the ST Amiga and probably early IBM PCs. And Acorn needed a compiler for this computer. And they went to a couple of Cambridge University academics, Arthur Norman and Alan Mycroft, of which the contraction becomes Norcroft. So you might see this seen online as the Norcroft compiler. And this was a toolchain that was on the Archimedes that developed software for the Archimedes. So moving the clock forward a bit, and what was ARM at the time was Acorn RISC Machine became Advanced RISC Machine, and ARM is span out of Acorn so that it can be used in other devices than the Archimedes. And of course, that toolchain has to evolve too. So just for a thing that, for now, I'm going to call the old toolchain ARMCC. It kind of had a brand name that changed multiple times over its lifetime, but I'll stick to just ARMCC for now. So ARM got its sort of early success in mobile phones and embedded. So obviously the toolchain has to be ported to Windows and the various Unixes of the day to be able to support that. Now, software development at that time was pretty much custom hardware, custom software. There wasn't really anything open source to write about. The Norcroft compiler was kind of like an early contemporary of GCC back in the 80s. So ARM had to concentrate on what the demands of this market were, which were principally code size. If you could save a bit of money on flash multiplied by millions of devices, you could save quite a lot of money. You'll also notice there that there's a printed manual and CD that these things came on. These were pretty much commercial products and tool chains at the time. So you were pretty much selling to companies rather than large user bases here. So as time went on, devices became more sophisticated, C++ became more of a thing, and ARM definitely didn't want to be in the C++ front-end business. That's quite a difficult challenge, and ARM's strength is very much in code generation at this particular point. So ARM licensed in the EDG front-end, if any of you had the fortune or misfortune to develop on Symbian, we were the platform compiler for Symbian, and that was pretty much all in sort of C++ at the time. Okay, so this toolchain worked quite well for this particular market. You noticed everything is pretty much fragmented. So there wasn't really any sort of common embedded platform to drive convergence. In fact, we only really had an ABI from 2004. But going through to the sort of late 2000s, everything was starting to change. So cost of producing custom hardware and custom software is going up. So what we saw at the high end, you were moving away from custom software towards an open platform, say something like Linux. And with that platform, you get a platform compiler like GCC, and it's very difficult to get anyone to change from that compiler. So you're stuck with a proprietary compiler that doesn't compile anything on Linux. It's not particularly useful in that particular context. It's still useful in embedded, but there are also other things changing here as well. ARMCC had a kind of weak mid-end but very strong code generation. But with the sort of more sophisticated process that would come along, that sort of code generation advantage was not being as relevant as performance. And that's where the sort of mid-end optimizations of compilers like GCCs were getting stronger. So we found ourselves at a point where we were behind sort of in code generation. The market was going towards open platforms. ARMs were also getting more powerful and starting to compete with other architectures in that area. And we felt we were a bit behind in code generation. What we really wanted to do was not do it all ourselves. ARM has a much wider partnership of companies that were using it. A lot of them had compiler engineers too, and it would be much better if we could work with them at the same time. Now, the GNU community was one area where we could do that, but the GPL was not a license that could work for all of the partners, so we had to have something else as well. And in about 2009 was our first mention of LLVM that I could find. And it was looked at as something that could solve a lot of the problems within ARMCC. So I'd just like to then now move on to what did ARM see in LLVM in 2009, which was quite early days at this particular point. So I'd like to break this down into technology and community. So on the technology side, LLVM had a modern C++ code base as opposed to a 25-plus-year-old C code base, much easier to work with, and could sort of certainly help solve some of the technical debt problems that we had. It was also strong where ARMCC was weak in the mid-end of optimizations. And it also, although it was early days in 2009, it did have some ARM support, so it was something that we could test out. On the community side, the license was favorable, so that meant that we could collaborate with other partners on code generation much more easily. And the modular design gave us the idea that, hey, could we plug in LLVM to our existing compiler? So I'll let you know in a few slides how that worked out. It was certainly something that was attractive at the time. On the weaknesses side, the technical bits were things that we thought, okay, these can get resolved. These are not critical. The community side was perhaps where the biggest risk was, because what we really wanted was a self-sustaining ARM community in LLVM, which it may sound obvious now with hindsight that this was always going to happen. In 2009, this was something that might happen in the future. So it was certainly not a given at the time. Luckily, it all worked out. Anyway, next slide, I'd like to look at the LLVM design that we had. This is not what got implemented. This is just kind of what the actual designs were. And we thought with the modular nature of LLVM, we thought, well, we're strong in code generation. We're weak in the mid-end. We have all our proprietary extensions at the front and customers that are using us. So what if we just swap out the middle end? And then we sort of, go in at the top, which, with our customer source code, convert to LLVM IR, and then at the end, convert back, and then go from the ARMCC code generation. That would give us the best of all worlds. Although then you've got the niggling bit about how do you write these bridges. The second bit, which we did implement as a prototype, was how do we compare LLVM to ARMCC? Now, back in 2009, Clang wasn't finished yet, so that was one of the other reasons that we sort of started with the EDG bridge. And this was where you start going in with ARMCC and then convert to LLVM and then just use LLVM all the way. And that would give us a chance to compare the two. And the final thing where we thought, well, if ARMCC's code generation really is that good, then LLVM might have more front ends. So we could, in theory, have C++ code coming in at Clang, and then you can then convert it out to ARMCC's code generation. So this all sounded really good, although it ended up being a bit more difficult in practice. So the next slide, I just want to show you what things were happening in the community at the time. Just sort of, the amount of time it took us to produce the prototype versus what was happening. So I took these from the LLVM community blog, which started in about sort of 2009. So moving this forward, we started in January of 2010, and then Clang self-hosted straight after that. MC, which is what we rely on now, was only really just started, only sort of embryonic in ARM support at that time. libc++ was announced, which was a really interesting thing for us, given that we didn't have a C++11 compatible C++ library at the time. A lot of improvements got made to the ARM backend, where we learnt the joy of merging from upstream to get those things here. And our prototype finished on about April of 2011. It was able to compile the various benchmarks that we needed to do to compare it to the original compiler and pass the Plum Hall conformance suite, which was important to us in terms of quality. Moving on there, LLVM got the register allocator. And then finally, final thing to mention was that we had the first European user group meeting, which was kind of like a proto-Euro LLVM, and that happened in London. Okay, so what did we learn during this time? Well, first thing was, I'd just like to refer back to a quote that, well, this is really a quote of a paraphrase that someone wrote in our internal sort of wiki page of their trip report to the 2009 LLVM Developer Meetings, Maintainers Roundtable. So I think it was a roundtable, so I haven't found any video of this. And I'll just read it out to you. Volatility of the C++ API is intentional. It allows for faster evolution of the design. It is a strong encouragement for LLVM users to contribute their improvements to the project. Any change not contributed is likely to break at the next release and will increase maintenance costs. And boy, did we find that out with the EDG bridge. So effectively what we had was two components, neither of which we owned, all evolving independently, and then us having to sort of do the impedance mismatch in the middle. And this was obviously not going to work at that particular point. So we also found that the code generation for ARM was quite a bit far behind ARM-CC at the time. This was not surprising, but it was something that we couldn't immediately act on at the time. But we also saw just how fast the community were moving, and at the points where the benchmarks that were more mid-end dominant were also much, much closer. So we could see where things were going. So that's where we had the sort of lessons that we had there. So one of the definitely things that we came there, that if we ever did move to LLVM, it would be paid to stay as close to the community as possible and not needlessly differentiate, because that would sort of help us in the maintenance costs going on. Okay, so one of the things we also found out during that time was just how quickly the LLVM community was growing, and like the GNU community was becoming important to ARM for Linux, it was also important that the LLVM community was going to be important regardless of whatever we did with our proprietary toolchain. So we joined the open source community. So at this point here, we weren't working on our proprietary toolchain. The people who were doing this were entirely just working on upstream LLVM. But that gave us a good start because it meant that we could increase our experience with LLVM, potentially build some influence in the community, or just learn how the community works. We sort of thought, well, what can we do most to help? Well, we already had a good, well-known assembler and disassembler. So we built a tool called MC Hammer to sort of essentially do some round-trip sort of assembly, disassembly to make sure that we could make all of the encodings correct in the backside. But that really helped us for that. And we also wanted to help build a community around ARM. One of the steps we did that because ARM is based in the UK, which was in the EU at least at one point back then. So we started the European Developer Meeting. Now that's sort of run on itself, but ARM was certainly helping with sponsoring that at the early time. Okay, so after a few years, we basically found that we had to support LLVM, we have to support GNU, we also have to support this old proprietary thing. But things were starting to fray at this time. Essentially, we were finding that there's just no way we could support 3 compiler tool chains to the level that we needed. One of them had to give, and it was always going to be the proprietary one at this particular point. That was the one with the most problems. So for embedded systems, we could go the GNU route or the LLVM route. The license meant that there wasn't really much of a choice in there. We also thought that LLVM was a sort of better base for an embedded compiler than the GNU one. So we decided to essentially try and swap out ARM-CC, which is the individual compiler in the tool chain, with Clang. And I just want to go through some of the design decisions that we made back in the time. So this is about 2014. So first thing was, and this is really a migration issue. So I don't know if any of you have tried to get anyone to migrate to a toolchain, it's like pulling teeth. It's very difficult. There's just almost always risk. And unless you're going to offer something they can't do with the original one, then you pretty much have, it's like, why am I going to bother doing this? So one of the things that we wanted to do here was, well, you don't need to be better everywhere, but if you're better in a niche, then we can start with that niche, and then we can start developing that, and then maybe move everyone else over later when we've got more experience. So what we chose here was that ARM v8, and in particular AART64, and C++11 library support were only going to be in the new toolchain. So that meant that if you were going to migrate to either of those, you were going to have some porting work to do anyway. So at that point, it was basically saying, new projects go to the new toolchain. Everyone else can still keep to the old one until the new one is better. And we were expecting that process to take between 2 to 5 years. Maybe 2 years to get to be better in one area, maybe 5 years to catch up. Okay. So we also chose the live at head model rather than sort of taking a sort of huge downstream fork that was updated regularly. Now, one of the main reasons for this was that we would, as ARM, we're constantly developing new architecture, new instructions, and those need to be upstream to LLVM. And if we're close to upstream, that process is much, much easier. It also means that you can do upstream first development, where if you want something in open source LLVM and the proprietary compiler, you just implement it upstream, it gets merged, and you pull it down the next day, and you don't have to do things twice at that particular point. It also meant we did get the benefits of the upstream features. The downside of this is that we would have to continually pay the sort of the maintenance cost of any downstream patch. Okay. So we wanted to minimize the number of ARM-CC specific extensions that were going to be in Clang. We tried to emulate as much of these as possible with macros and inline assembly, that type of thing. Essentially just trying to keep the downstream patch down. However, benchmarks are important, particularly for processor companies. And in our case, it was Embassy and Drystone, Cormark, that type of thing. And there was kind of a mini benchmark war going on in Cormark at that particular time. And it was very important to get good scores on that. But that's the sort of thing where it's not always easy to upstream those changes. So we needed to focus on that. And we also made the decision, well, it wasn't really a decision because it wasn't really an option at the time, that we were going to have to share our original bin utils and libraries with the proprietary toolchain. And this is primarily because LLD, I think, was only at its very, very earliest stages at that point. And it was certainly before the ELF-COF split. And LLVM libc didn't exist. And the bin utils that we use now were really developer tools rather than anything that you put up in front of a user. They were, when I say developer tools, they were LLVM developer tools, not real developer tools at that particular point. Okay, so here's just like a little picture of how things ended up, where you have on the left-hand side, ARM-CC, we had the Rogue Wave C++ library that we'd licensed in, but that wasn't going to get C++11 support. And then you have the various bin utils and libraries. They would get transplanted across because we were essentially sharing these between two tool chains. Now, this had some negative aspects in that we always kept these things free of LLVM technology, which meant that we'd essentially had two separate technology bases, which I guess protected you from some upstream diffs, but it also meant that if anything upstream changed, you would have to sort of make corresponding changes in your downstream, which cost us a lot in the end. Now, for example, for link time optimization, we were probably one of the few people who actually used LLVM-LTO.so rather than just importing the code generator directly. Okay, so next thing, I just want to make a little bit of an aside about upstreaming and proprietary changes. Because while you can say, well, yeah, the bin utils weren't there, LLD wasn't there, well, could we have helped there? Could we have tried to develop at that particular point? Could we have tried to upstream some of the downstream patches that we'd done for things like Embassy and Cormark? So one of the things to just put out the quote that I pulled out before, any change not contributed is likely to break at the next release will increase maintenance costs. But if you're in a niche, the community doesn't always want your changes because upstreaming is not a gift. It's really asking the community to take on the maintenance burden of that change forever. So the upstream has got to be able to understand that change, and the additional complexity has to be justified. And if it's a niche area, like say, for example, at the time, embedded systems, and most of your upstream developers are on, say, desktops or servers, then they've got to work extra hard because they've got to understand the change, which is in a different technology area that they're in. And they may not even know why it's important in the first place. So it can be quite difficult at this particular time. And so this is my sort of observation of embedded tool chains at the time, because we found out we weren't the only company doing this. But if you look at the sort of typical model of an embedded tool chain, is you have a Clang-based compiler that people have bolted on, and then it's got its own proprietary linker, it's got its own proprietary C libraries. They've all got their own code size focused optimizations. They've got their own C extensions for embedded things, and there's no standard for this. Everyone's done things on their own, often not in a not very principled way. And there's not really a common software platform, a driving force to force people to do the same thing. And there's one of these things where if you were going to upstream this, you'd have to account for everyone's different way of doing it. So it would probably cost you about 10 times worth the effort of just making a small downstream change. So I think in the end, people made the pragmatic choice and stayed downstream. Now, when I say there's no software platform driving conversion, that for us, that was just not yet. So move the clock forward probably around about 2018, something like that. We started to see a resurgence of what I would call embedded software platforms. So whilst you might have something like Linux sort of driving things forward on the desktop side, you have things like Zephyr, FreeRTOS, trusted firmware, all these sort of open source embedded projects that people can use. And of course, being open source, these naturally need an open source compiler, and that's what they base all of their infrastructure on. And at this time, it was the GNU compiler. And if you don't support the GNU compiler interface, or the GNU linker scripts and the bin utils, then you try compiling some of this stuff and it's just going to break, or at least someone has to port it. And we were seeing increasing support comments saying, hey, I tried to build this thing from this open source project and your compiler didn't work at that particular point. So it was clear that open source in embedded software was becoming more important, and we needed to do something about that. We also found that because we'd invested in the LLVM proprietary toolchain to get the best out of code generation for embedded systems, LLVM had ended up with better code generation than GCC for some of our newer microcontrollers. So we were facing a demand of how do we get that out to customers, and we needed LLVM open source rather than proprietary, because we needed something that was going to work for all of these. Now, at this particular time, to do that, you kind of had to try and hack it together with an existing GNU toolchain to fill in all of the linker and bin utils and libraries. But in a sort of serendipitous act, the community had ended up fixing a lot of the things that made it possible for an embedded toolchain fully LLVM to come through. So on the next slide, I just want to perhaps thank the community for a lot of the work that they did on the linker and bin utils. So this is really not the embedded community doing this. This was companies like Sony, Google. I probably forgot some more that worked on this to really make the bin utils to be actual production ready that you could put in front of people. In particular, LLD got great support for linker scripts during this time. I particularly want to call out Clang-built Linux here, because really the Linux kernel is just a giant embedded system. It's also a very demanding embedded system that makes high demands of tools. And if you can reach the bar of being able to build the Linux kernel, the chances are you can build pretty much any embedded system with a small amount of change. So I think that was one of the key enabling factors to getting an embedded toolchain done, was the work that was done for the Linux kernel. Okay. So to make this work, we were able to produce this thing called the LLVM embedded toolchain for ARM. So this is really just a set of build scripts that would check out LLVM, check out a open source C library called picolibc. LLVM-libc at this time didn't really have any plans for embedded support. This was kind of in its early days. And we ended up putting this together. Main weakness was the lack of multi-lib support. So multi-lib is kind of where, for those of you who aren't familiar, is where the linker driver on the compiler will look at your command line options and say, oh, I see this person has used this hardware with this calling convention. I'm going to use this particular directory to pick up the libraries. So if you're on, say, a x86 machine, you might compile the 386 and get the 32-bit libraries of the 64, so you have two multi-lib variants. Now, if you're a toolchain for the whole of the ARM architecture, you might have hundreds of multi-libs because a lot of these combinations just geometrically multiply, where you end up with things like an architecture choice multiplied by floating point choice multiplied by C++ exceptions choice, that type of thing. And because we didn't have multi-lib, we had to use config files. So we ended up with, like, our initial release had 33 config files that you would have to use to target the right thing, which is obviously a little bit too clunky for production, but it kind of just about got enough here. Now, one of the advantages that producing that toolchain gave was it helped us find some other people in the community who were also working on similar things. It also meant that we could advertise this at conferences, things like FOSDEM, EMBO 2023, where we could go out and say, hey, we've got this open source toolchain, you can build it. And when people asked on Discourse or the mailing list, how do I build this thing? You can say, oh, just go to that project. There's a CMake. You can probably adapt it to make it do what you want. So I think that was a good first step on the way here. We also started the community call. This was sort of, I think in about 2022, where we sort of coordinate reviews and RFCs, where we found many other members of the community all working towards a simple goal. And I think when I go back a few slides to where I said that the embedded community was a bit fragmented and we didn't think that we had enough sort of upstream support to get patches in, well, we think things were about to change at this point because we've now found other companies all working for the same sort of thing and who are willing to review the patches and drive some things through. So I think this was a really, really good start, and I noted that many other similar sort of communities have now started calls, and certainly for any of you who are in a particular niche, I encourage you to look at the developer diary and try and figure out, has anyone started a community call in your area? Do join that, it's a really, really good place to get started. Okay, so the final sort of slide on the sort of proprietary toolchain was, well, we've been working towards this LLVM embedded toolchain for ARM. We've still got our proprietary toolchain. And yet we're in the situation again where we've got three toolchains. We've got GNU, we've got LLVM, and we've got this proprietary LLVM embedded toolchain all again. And we're sort of getting to the situation where we can't put enough resource into it to do all of these well. So one of them is going to have to give. And we're essentially here making a bet that these open source platforms are going to become more important as time goes on versus the sort of proprietary interface that we had before. So even though we're probably losing a bit of code size and losing some of the embedded specific features we had in our proprietary toolchain, we think the sort of key selling point for the new toolchain is, hey, you can go to these existing open source software platforms and build them with LLVM. And we're hoping that in the future, we'll be able to bring in some of the features that the LLVM toolchain has for other developers like sanitizers to embedded, and that will become a sort of key feature for the platform to moving forward. And then one of the later things we want to do is adopt LLVM libc as the C library, because at that point we can just build the whole toolchain from one particular point. Okay. So here's my sort of last sort of slide for where things went from ARM Compiler 6, which was the proprietary toolchain. So here we had the Clang compiler and LLVM C++ with the proprietary bin utils. Now it's all LLVM apart from Pico libc at the bottom. We do have LLVM libc as an option right now. It's kind of like a, hey, you can use LLVM libc if you want. Ideally, we want to reverse those positions so that LLVM libc is the default, and then you say, hey, you can use Pico libc if you want. So we're excited to, to work on that and make that something real in the future. Okay. So to conclude, what are the main things that we've learned in about sort of 15 years of contributions? So first thing I'd say is that if you can find an open source community that's aligned in the same direction that you want to go, they're going to go a lot faster than you. So downstream development is probably what I'd say is low latency. You can make decisions fast, but upstream is much, much higher bandwidth because there's a lot more developers there than you have. Now, one of the things that you might have to do is, well, what if the community is not going in the same direction that you want it? And that's where you have to, I guess, resort to community building. And that's where you need to find the community. Certainly, it's one of the things you could do there is look at discourse, come along to conferences like this. You've all made a good start here. Try and find people who are working in the same sort of niche as you. Are you able to, say, start a regular meetup group? Are you able to coordinate reviews, that type of thing? Are there any sort of shared areas you can do? And if you can't find an exact match for your community, can you find an adjacent one with similar goals? As I mentioned before, all of the LLVM bin utils work and the LLD linker script work was not done by the embedded community, at least not at first. It was done by other communities with other goals, primarily Clang built Linux and that type of thing. So if you can find common goals with adjacent communities, you can still achieve what you want to do at that one. And finally, when we first started in like 2014, we felt we were one of the only ones doing embedded development. Now 2025, there's a whole community around LLVM embedded development. So communities can change over time. So even if you are alone right now, you might not be in the future. So it's still worth keeping up with the community. Try and nudge it in the direction that you want to go. Sometimes it just takes one company to put its head over the parapet and say, hey, we've developed this, and then others can jump on from that point. Anyway, that's been our journey. It's probably not universally applicable to everyone. There's sort of plenty more other stories that can be told in this area. We'd certainly love to hear other people's stories of how they've migrated away from proprietary toolchains. So, okay, thank you very much.
If there's questions, there's a mic front here and in the back, and I have a handheld one I can bring to you as well. So, any questions?
I noticed you said a lot of toolchains had proprietary linkers, and in general, it feels like it's a lot more common to see proprietary linkers than proprietary compilers even now. Do you think there's any fundamental reason for that besides just linkers being simpler in some senses than a whole compiler, so like it's easy for people to have their own or maintain their own?
I think that's certainly true in that almost any toolchain team can build a linker if they need to, probably with maybe one or two people and to maintain that. I think linkers are also the point where they're the confluence point of all sorts of things coming together. So if you do want to do something that's across the whole toolchain, you're probably going to need to do something with a linker at that point. I mean, I think linkers are also, they seem to accumulate all of the cruft of all of the architecture and all of the compiler. You just sort of fix things up in the linker. So I guess that's probably why they often end up being proprietary. I think also, if you've got a tool chain that's got its own C libraries, if all of the components are aware of each other, you can do optimizations for that are sort of hidden or need link time stuff at that point. Okay.
Hey Peter, not so much a question, but I just want to emphasize that you could probably file off ARM and put Sony on most of this talk, okay. And our experience would be nearly identical. We were starting from a proprietary toolchain, EDG-based. We tried to glue EDG onto LLVM. I think we had much the same experience you guys did. But finding the LLVM community, the licensing, just the trajectory that it was on, It all feels very familiar. And so it's not just embedded developer, embedded environment where this works. I mean, this is great. Everybody, any other platform vendors out there? Same story, yeah, with the VMS, yeah. So take this lesson, people.
Okay, thank you.
Thanks, Peter, for the great talk. I have a question, which is, a lot of projects have like gone from GCC to like Clang coding.
Yeah.
One of the common problems that I was also discussing with some people in the community here was just to like switch the compiler front end. It'll be nice to have a bunch of tools upstream that could identify common patterns, deal with warnings and so on and so forth. Have you kind of like, one of your slides mentioned about like building tools for like moving people to like the open source tool chains. Have you built any tools from your side to like help with such things? Like
migration tools or whatever? Yeah. So I think we started with an assembler. Can you move your assembler across? I think we focused on documentation rather than automatic tools. So we had because one of the advantages of a commercial tool chain is you have commercial documentation. So we had a sort of migration guide put together with a support department for, if you're using this flag, then this is the closest equivalent, that type of thing. So I think we chose the documentation route rather than the source code route. I think we found that a lot of these extensions they were kind of concentrated in certain areas. So for the most part, it wasn't really needed. It was we kind of relied on the human thing rather than the tools. I think it may also be a degree of, were we sophisticated enough to build those tools at the time? I think now with Clang, you might be able to use Clang tooling to just automatically do those sort of things. We probably weren't good enough with Clang at the time to think of that approach at the time, but I think that might be something that could be done. The linkers are a bit harder because often the proprietary links have got very, very different formats for their linker scripts, and they're not identical. You can't just do a one-to-one translation with a tool at that point. I think that's just going to have to be human help at that type of thing.
Thank you.
Hi, Peter. Thank you for the great talk. So you mentioned that you're still working on maintaining not just the LLVM compiler, but also the GNU compiler, and you've been doing that for quite a while, like over a decade. I was curious on the GNU side, are there any things that perhaps worked out better, not just on the technical side, but perhaps the community, like anything that we could improve on, could you contrast the two? Like, what was your experience?
Well, in terms of the GNU community and the LLVM community, I'm trying to think here. And I think that's really stumped me there. I haven't actually got a good answer for that one at that point. I mean, I think the LLVM community, I'll just say at the moment, I've always found the LLVM community very welcoming, and it's been a pleasure being able to sort of try and connect to people. I guess the thing that we found the most difficult is, I got the impression, I knew when you post up on something and say, hey, RFC, should we do this? The hardest bit is when you don't get anything back or whatever. I guess it's silence or whatever. It's often better if someone says no rather than doesn't say anything. So I think a lot of, if this could do anything better, I would say is please do, if you see an RFC that's right in the area, it's so easy for that to just fall off the discourse thing. Please do leave a comment, subscribe, keep reading, keep pushing it forward, and I guess comment on reviews. So I guess it's more, please come out of the woodwork if you think this might be useful. Don't just let it happen. That would probably be my best guess at that. Thank you. I think I've got 15 seconds left, so I probably...
Any final questions? All right. Thank you so much, Peter.
Great, thank you.